Welcome to lecture 16, the last one in this course. This lecture is on structured illumination microscopy, and the idea of this last technique is to use illumination patterns to excite the sample fluorescence. It's a fluorescence technique like the two other super resolution methods that we talked about in the previous lectures. And by doing this, you can get access to high frequency information inside the sample through generation of so-called beat patterns, so-called frequency beats. And the technique is in many ways possibly possibly the most powerful super resolution method we have today. It is not because it has the highest resolution. You can, in principle, get a higher resolution with single molecule localization microscopy and with STED. However, it is by far the fastest method, and it strikes somehow an ideal compromise between speed, which you need if you look at living systems, and resolution, which is to look at small detail, of course. And the technique is beautiful because it really encompasses most of what we've learned in this course. I will, with this, go to my presentation and show you the title slide here, which has on it the inventor of this technique, SIM, or Structured Illumination Microscopy, Mats Gustafsson. In my view, he would have been very deserving of the Nobel Prize. Unfortunately, he died before that was possible for him, far too early. I mean, he died before he was 50. But he published a seminal paper on this, and not very much has been said since he published this paper, and on structured illumination microscopy. And so the idea is that you generate what is called moire patterns, super resolution via these beat patterns or moire patterns. So let's go and take a look at this technique. So to understand what we do here, I want you to first consider this image here of Albert Einstein. And you know by now that image information or sample information is conveyed in spatial frequencies. And so let me turn on my mouse. So if you look at this face of Einstein, you see that his hair, you would expect there to be high spatial frequency content here. And that is because of course the image very quickly goes from bright to dark, from bright to dark, from bright to dark. If you look at the skin here, there's low frequency information, although he's got these creases here on his forehead, and perhaps you have a spatial frequency associated with that of 1 per centimeter, or 1 inverse centimeter, because you get this fine line, this pattern, changing in this direction, in the direction that my mouse is moving right now, the laser pointer is moving. Perhaps it changes once per every centimeter or so. Again, you have high spatial frequency down here where the moustache is, and so on. And of course, what the microscope does, because it has a limited optical transfer function, not all spatial frequencies are passed through the instrument, so high spatial frequency content is lost. And to mimic what that might do, I want you to do the following experiment. Look at this picture and then squint at it with both eyes nearly completely closed, or close them completely and then reopen them just a little bit, just enough, so you admit a little light. Make the image that you can see with your eyes as bad as possible. And when you do that, you will see a picture of a woman, in fact. And the woman is Marilyn Monroe. I hope you can see that. You have to play a little bit. But if you have glasses, take the glasses off, squint, and really hardly admit any light. Try to make the image really poor, and then you see this happening. And the question is, why is that? Why is that happening? In fact, this image here consists of two images. It's Marilyn Monroe's face and Albert Einstein's face are superimposed on this image. And when you degrade the image, the high spatial frequency content, i.e. here, around here where the hair is, where the mustache is, disappears. You cannot see the high frequency detail anymore, and then you get what is below is Marilyn Monroe. It's much smoother skin. Obviously, she doesn't have a mustache, and so this face then turns into the underlying Marilyn Monroe picture. Another way that this happens in the microscope, if your sample is sufficiently small, this happens automatically. So you can see the spatial frequency information is now disappeared, and you get on your screen now only what passes in the spatial frequency window that is actually transmitted. Now you have you sacrifice the high spatial frequency detail first once you reduce the object down. Now the question then is, in a microscope where you have diffraction and where high frequency detail is lost, you can't do anything about it. That's diffraction, that's what it does. How is it possible to transmit high spatial frequency detail in the presence of diffraction? And that is what structural illumination microscopy does through an ingenious trick. And to illustrate this, I would like you to consider this cartoon experiment here. So on the left you have a shirt. This shirt here has low frequency detail, so it corresponds to the previous image of Marilyn Monroe. So you have in this direction, let's call this the X direction. So along X, the spatial frequency is perhaps 2 per centimeter, 2 inverse centimeters. So you have 2 lines per every centimeter, because every 5 millimeter you have a blue line coming down here. So in this direction, the intensity varies by about 2 per centimeter. What is it along the Y direction? Well, along the Y direction, it's obviously 0, okay, because nothing's changing if I go up in this direction here. So in fact, this shirt can be pretty well described with one spatial frequency, which is 2 lines per centimeter, and you get the pattern in this direction, and you don't do anything in the Y direction, so that gives you the set of vertical lines. On the other hand, Albert Einstein encodes very high spatial frequency detail. You see this shirt here. Perhaps here you have 3 or 4 lines per centimeter, perhaps even more. Maybe it's 6 or 7. I don't know exactly, but it doesn't really matter. But you see it's much higher than the corresponding shirt from Marilyn Monroe. And of course, you can imagine that this high spatial frequency detail here on that shirt will disappear much sooner than it would on the shirt on the left. If you squint your eyes, or if you stand far enough back, or if you make the image small enough for this shirt here, then of course you can imagine that all these lines disappear, and you just get a homogeneous bluish color, right? Because you can't differentiate spatial detail. So the question is then, if you have an instrument that wouldn't resolve these lines, how can you pass information that corresponds to the spatial frequency through the instrument anyway? And the trick is ingeniously simple. And like all very good ideas, the idea is that you illuminate the sample. So consider these lines, these blue lines here, to be fluorophores arranged in these lines to give you the pattern. Let's excite these fluorophores now with a structured illumination pattern, like the one shown to the left. So here, the illumination light goes from dark to bright to dark to bright, and at a very high spatial frequency, as high as you can transmit through the microscope. So you project this pattern onto your sample, and let's see what happens. When I do this, what happens, and I hope you can see this in the film, you see now that you get frequency beats. The spatial frequency of the shirt now beats with the excitation spatial frequency and produces these patterns here. And these are moire fringes, as they're called. Once you know what they are, you see them in nature all the time. You know, you can see this when you, for example, have gardines folding over each other. So you can't see the fine pattern because they're too small when you stand far enough away. But when they sort of move against each other like this, you can see the beat pattern sometimes, and there appears these bands, like you see the bands here on this shirt. And it is easy to understand, of course, that these bands convey information about the underlying structure. The idea of structured illumination microscopy is to record these low frequency beats that you can clearly see, and then you use, if you know what the excitation pattern was, you can use Fourier tricks to get the original pattern back. That's the idea of structural illumination microscopy. One takes images at different orientations of the illumination pattern, so you generate beats in different directions, and that is of course to probe spatial frequencies also in all the different directions, because you could have high spatial frequencies in this direction, high spatial frequencies in that direction. So if you want to probe spatial frequencies in this direction, you need to have your pattern pretty much aligned with those spatial frequencies, right? So a pattern like this wouldn't probe spatial frequencies in this direction very well for obvious reasons. So perhaps that's something you want to think about and see whether that makes sense in your head. And so the idea is then I somehow generate these frequency patterns, I understand what the beat patterns are, understand the physics of it, and then I go back and use the computer to calculate from the beat patterns what the underlying sample patterns were. And with that, I would like to now turn to the paper visualizer, and let me just turn this on. Yeah, I'll go out here so you won't lose focus. Let's just see that I image formation. I'll just focus this. So is that focused? Yeah. Okay, so let's go back to the basic problem of how an image is formed in a microscope. So if I have an object, and the object has a we look at a 1D case here, has a fluorophore distribution along X that is described by a function like this, and I illuminate this now with a pattern, then if the excitation intensity is described by EIX or IEX as a function of X. So this is the illumination pattern that excites the fluorophores, which are arranged as such as this function this function here in the object plane is describing. So that would be the resulting fluorophore emission in the sample plane. So the fluorophores in X will be excited with a modulated pattern like this, and of course the two things are product. Where this is bright, this will excite the fluorophores in the object plane, the sample plane a lot, and where this is dark, it will suppress the fluorescence. So it's a product of those two things, which gives you the emission from the sample plane. So that's what goes towards the objective now. So what this is, it's a multiplication in real space. And in Fourier space, we know that the spatial frequencies of this are given by the Fourier transform. So we are now in spatial frequency space, and that is given by the Fourier transform of the object function kx. Sorry, it's the Fourier transform of the object function convolved. So this should be a k, convolved with the Fourier transform of the excitation pattern kx. Okay, let's make that clear. Kx. So k is of course the spatial frequency. So if I were to sketch this, then perhaps I have let's make an object which I just symbolize. Let's make this, so this is x, and this is the object, the sample function. Let's make this something like that. A cell. Of course, this isn't a proper function as such, but you get the idea. So the real object may be a cell, for example, with a nucleus, something like that. It doesn't really matter, which is labeled with fluorophores, anything. And now we let's illuminate this with a sinusoidal excitation pattern. So let's do this. So this would be I Ex of x. And so this is again in real space. So the illumination pattern may be a cosine like so. And the emission pattern in real space is of course a product of the fluorophores times their excitation. So what is that now in Fourier space? In Fourier space, this same thing will be now as a function of spatial frequency. And so this is the Fourier transform of the object function. This is the Fourier transform, this is kx. This is the Fourier transform of the excitation function. And so let's suppose the spectrum for this cell here. This cell has a spectrum, a frequency spectrum that may be something like that. Doesn't really matter. Let's make it like this. And of course, what is the Fourier transform of this function? Well, it is offset from 0, so there's going to be a DC component. And of course, this has a frequency. This is a cosine, so it will have components at k0 and minus k0. Okay, something like that with lower amplitude, but you know all the reasons for that. And of course, in Fourier space, this product turns into a convolution. Okay, so what does that do? I mean, you know what a convolution does with a delta function. So essentially, this function convolved with that delta function is just that function again. And this function convolved with that delta function is just a scaled version of this function, shifted to be centered on this delta function, and similarly on that one here. And so what this will result in is, if I draw this, something like that. You will have your central delta function, and you have this one here and that one there. So the first thing you get that original function sitting here. Okay, and then you get a copy which is scaled, so that sits here. It's a bit smaller in intensity, but otherwise it's the same. And then you get another shifted version of the spectrum sitting here. So that looks pretty messy, right? And it is. You saw the patterns from the shirt. These beat patterns, they don't look really like the underlying shirt itself, right? And that is because this whole thing is convolved with so the functions are now overlapping. And so why do I do that? Why do I generate a messy picture like that? So this would be the emission. So this convolution then turns out to be the spectrum of the emission of kx. Well, I tell you why. If you think about what a microscope does, of course it has an optical transfer function, and so some of the high spatial frequency content doesn't pass. Now, if I draw on top, if I draw the optical transfer function on top, OTF, you see what happens. This tail here, so if I draw this here, this tail and this tail, these high frequency tails, are lost. And it's that process that caused, of course, Albert Einstein to disappear, because his mustache and his hair were somewhere encoded in frequency detail out here. And these frequencies here were much stronger for Marilyn Monroe's face, and so that's what shone through once you clipped those ones out here away. And so what does that then do? If I actually illuminate with this structured pattern and I actually now get this convolution, well, let's look at this picture down here. If I draw the same thing, but of course of this resulting mess here, only this will be passed through. Only what will actually pass through the optical transfer function will make it through the instrument. So what have I won? Well, you can see this now very clearly. In fact, by doing this trick, this tail here has now shifted into the passband of the microscope. And conversely, this tail here has been shifted into the passband from this other side, simply by putting copies of this original spectrum and displacing it. You're shifting this thing into the passband, and shifting it the other way shifts this part in, and therefore you get extra high frequency content into the sample. Now that is so what you see in green here would be in green, what you get is the emission frequencies, which is the so that's kx, so that's the spectrum, that's this original spectrum here, which you get through this convolution here, but it is multiplied by the OTF. That's what passes through the instrument, and that contains now extra frequency detail. So the key is high frequency detail is now shifted into the passband. The problem is that the resulting picture is a mess. This convolution operation has sort of mixed all the spatial frequencies. So these lower ones of the original function are now mixed with these other ones here. And somehow we need to separate those and put these into the right place. We need to somehow separate these spectra and put them into the right place so that we can assign this tail here to be in the correct position, this tail here to be in the correct position. And once we essentially generate this new spectrum that has all the components back in their right place, if we can somehow untangle this, that's the operation in SIM, that's what we need to do, then we can get a better resolved image, because then actually we are reconstructing this function here. So what we need to do is we need to actually shift components, and we need to scale them and then patch the whole thing together, and that's how we get the that's the operation that we need to perform, and one performs this in Fourier space to do structural illumination microscopy. This is the exact physics of the technique. Of course, the detail here is quite a lot of math. So it's quite computationally intensive to do that on real imaging data. And of course, we don't go through the whole details of it, but we know enough to understand the principle of the technique and to understand how it works. To give you a bit more detail on this, let's look at this this process by taking a sample illustration, taking a sample that looks like this. Let's suppose I have a sample, and along X, I place a number of fluorophores. Here, so you got a fluorophore sitting here, and then one here, and one here, one here, and one here. And then each one of those fluorophores we now illuminate. We illuminate this in a wide field microscope. So I indicate this by a light field that is everywhere. So this is the illumination. So this is wide field illumination. So everything is illuminated homogeneously, and then what you get, this would be a standard microscope setup. So all these fluorophores now have the same excitation intensity. So this, so we call this IEX. So the emission now will be the sum of all the PSFs from these individual fluorophores. So let's draw this one. This one will have a PSF like so, and this one perhaps something like so. And this fluorophore here will have a PSF that may be like this, and so on. I just draw this in, and this one will have something like this. And then, of course, the overall signal is just the sum of all these intensities, and that will give you perhaps an overall signal that probably looks something like that. That's the overall signal. And this will, of course, be the case because when these fluorophores are sufficiently close to each other so that you don't resolve them, and so that these individual point spread functions really can't, they're closer to each other here than lambda over 2NA. Right, so that distance is smaller than lambda over 2NA. And in that case, you don't resolve them anymore because they bleed into each other. So now, so this is wide field illumination. Let's take that same example now and let's illuminate it with something else. Let's take the same sample. Let's do this. Like so. And now let's illuminate this with a pattern, and let's make that pattern perhaps something like that. Okay, so when we do this now, we remember from our fluorescence lecture that what we get, the fluorescence signal, is proportional to the intensity that you put in, to the excitation intensity. So you will get this fluorophore will emit more brightly than this one. This one is not excited at all because the illumination intensity is 0, and so on. So when we do this now, we draw the point spread function. So this one here will be quite large, because it has a lot of light. This one has slightly less, so let's draw something that's slightly smaller than that. And then here too, so this one here will perhaps be something like that, and this one here too. And then the overall modulation that you get looks something perhaps like that. So you get the idea. So this here is the structured illumination. And you make the period of the illumination as close to the maximum spatial frequency that you can transmit through the microscope. So you want this period of this illumination is close to lambda over 2NA. That's what you aim for. So you want to put the highest spatial frequency onto the sample, and that gives you the highest spatial frequency in these beat patterns. And so you can already see that this contains extra information. You have already got more information than before because there is a modulation, and that modulation tells you that there's something going on in here that these fluorophores that has to do with the way that these fluorophores are arranged down here. So the overall amplitude here is a reflection of the underlying fluorophore distribution and, of course, of the way that we illuminate the sample. Okay? So you can see that this tells us something, but of course this isn't enough to reconstruct the sample. There's obviously not all the information in that red trace yet. For example, if you look at that fluorophore, you don't have yet any information about it. You didn't excite that fluorophore, right? So it is kind of intuitively obvious that what you have to do is you have to shift the illumination pattern. And you shift it, in fact, by you shift the phase of this illumination pattern, and you take images with the pattern displaced several times. And in fact, what it turns out that if this wave here is a sine wave, this illumination wave, then you need 3 images, 3 phase shifted images. And typically one would shift these at one would have the first image with phase 0, let's say, and then we have 120 degrees and 240 degrees, or 2 pi over 3 and 4 pi over 3. So you have the first one at 0, then at 120 degrees, and at 240 degrees. So my question to you is, why do you think I need 3 images? Think about this for a sine wave illumination. And does that make sense? And why do I arrange them to be at these angles, 0, 120, and 240, or 0, 2 pi over 3, and 4 pi over 3? So if you look at that picture carefully, then perhaps you see that. So once you've done that, let's say we've taken three such images. So we take one like this, we get this modulation, and we shift it along. Maybe the modulation changes a little bit, and then we take it along, it changes again. And so we record the corresponding moire patterns, these beat patterns, and then we use Fourier techniques to get the frequency spectra corresponding to these images back to the right place. Okay, well, so let's have a look. If I go back and look at a spectrum of a sample again, let's have a look, and let's make this spectrum look again. Maybe the cell has a spectrum like this. Then I have an OTF. The OTF passes only this part of the spectrum, right? Now I multiply this with the illumination spectrum. Sorry, I convolve this because we are now in Fourier space. So this is Kx and Kx, and this is the illumination, IEx, Fourier transform, Kx, and this is the object of Kx, object Kx, Fourier transform of it. And that convolution, of course, so what it does is so we have this this spectrum as we had before for a sine wave. Now let's look at what might happen at a frequency here. This one's outside the passband. Let's call that K1, and let's call these frequencies plus K0 and minus K0. Then by the convolution theorem, of course, you get a copy of this spectrum situated here. So you're going to get one copy of K1 to be here. So what you'll end up with is you're going to get something that is K0 plus K1, and that is definitely not going to be passed through your instrument. So that's a sum frequency, you can see. But you can also get the difference frequency. With this one, you get a component that is K0 minus K1. So it might lie somewhere around here. And that's the one. That one here is K0 minus K1. Can you see that? Why that's happening? So you work that out from the convolution theorem. And of course, that's precisely what we showed on the first picture when we shift the spectra around, right? So this one here comes from the copy of this spectrum that is placed on over here. Okay, so that's how that frequency tail comes in there. And then, of course, if you think about it, what's the maximum K1 I can still pass through the instrument? And it turns out that that will be determined by how large K0 is. The larger K0, the higher the spatial frequency I can put through. And the biggest K0 I can put in is at the limit of that optical transfer function. And that is, of course, given by whatever lambda over 2NA is. Okay? So that is what that is, what that corresponds to. And it turns out that the resolution is then maximum resolution I can get. It shifts from so you get it shifts from it shifts from the usual lambda over 2NA to lambda over 4NA. So now you can actually look at things that are 2 times smaller in separation than was possible before, right? So you, for an illumination at lambda over NA modulation, 2NA, you can resolve fluorophores at lambda over 4NA using this trick. So you gain a factor of 2 in resolution. Now, you may say, well, that's not very impressive. We talked about things that had 10 nanometer resolution, 20, 50 nanometer resolution with single molecule localization microscopy and with STED. And here we're talking, what, 100 nanometers perhaps, you know, maybe I go down from 240 nanometers for a normal PSF down to 120 nanometers. What's so impressive about that? Well, first of all, you gain that resolution in X, in Y, and you can gain it in Z too. And so if you have a voxel that has a certain volume, V, then if you think about it, factor 2 by 2 by 2 gives you a factor of 8, almost a factor of 10 reduction in the voxel size. And that, for many imaging applications, is more than enough. The other thing is that you only need 3 images per direction. You actually have to change the orientation 3 times as well. But you only need, in total, perhaps 10 images to get one super resolved image. So if you compare that with STED, where you scan a tiny point, pixel by pixel over the image, which takes forever, and even worse for the single molecule localization microscopy image, where you have to take tens of thousands of images to generate one super resolved image, you're gaining here massively. And as I said, the trade-off between speed and resolution seems to be almost optimal in this technique. And again, our general principle applies. You gain resolution by switching molecules off, right? You're switching that one off, for example, here. And that's, by suppressing that, you can get more information about the other ones. That's the key, as has always been the case. So I will make a break here, and then in the second part of the lecture, I show you how it's done in practice.